All right, hi guys. Hope you guys are doing well. So we spent a little bit of time looking at circles and getting an understanding of that, and today we get to talk about the ellipse. Now, the ellipse, as you saw in the video from prior, we get by slicing the cone. Okay, kind of the video guy in the video said askew, kind of just say kind of diagonally across the cone, and we get an oval, and the special type of oval that we get from that is called an ellipse. Okay, but let's develop this, and I want to go back to the circle for a moment here. So let's think about the circle, and let's think about our standard form of the equation of a circle. We have x squared plus y squared equals r squared. Okay. Now, what would happen if I were to divide both sides by r squared? Okay. I would get the equation x squared over r squared plus y squared over r squared equals 1. Okay, and feel good about that. Okay, I hope you feel good about that too. Okay, let's go in and let's graph in Desmos the equation of a circle in this kind of different form. Okay. Let's graph x squared over, let's pick a radius here. Let's pick a nice radius like 3, so r squared would be 9. So if I did x squared plus 9 plus y squared over, did I say plus 9? X squared over 9 plus y squared over 9 equals 1. Okay, we get to see that circle with radius 1. But what happens if I take this and I change it to something else, like a different perfect square such as 16? Okay, we notice that it is no longer a circle, and this is now an ellipse. Okay, and what I want you to think about here is I'm going to first make both of these 1. That is a circle with radius 1. Well, if I make that a 4, I did what? I just horizontally stretched it by 2, didn't I? Right? It was at 1, 0. Now it's at 2, 0. Okay? And the way I can think about that is I can rewrite this like this. And we know, thinking about how graphs of how transformations, equations, wow, I'm stumbling over my words here. How when we have our equations, we can manipulate them to do our transformations. We know if we're dividing by r, which is the same as multiplying by 1 over r, inside with the x, that is going to do a vertical stretch, isn't it? Okay. We are going to stretch this out actually by r. Just think, if I had a 1/2 in here, you guys would tell me that's going to vertically stretch or horizontally stretch the graph by 2. Well, that's the same as writing x squared over 4, right? 1/2 squared is 1/4. X squared is x squared. That's x squared over 4. So we can see in here, when I put that 4 in there, it horizontally stretched it by 2. Well, it's going to work the same way when we do it with a y. If I put a 9 here, it's going to vertically stretch it by a factor of 3. So if we stretched out this axis by 2, we've stretched out this axis by 3, and we have an ellipse. All right, so that's kind of how I like to build this off, is it's really closely related to a circle. In fact, we could write the equation of a circle using the equation of ellipse. It's just the bottoms have to be 1. So I've got a bunch going on this page that I'm going to talk you through. So the standard form of the equation of ellipse is x squared over a squared plus y squared over b squared equals 1. Okay. Now, what that does is it horizontally stretches what we call the major axis by a factor of a. So we're at 0, 0. 1, a comma 0, and negative a 0 are called the vertices. So this is 1, so I should just write vertex. So this is a vertex. This is a vertex. Okay. It stretches the vertical axis, which is what we call our minor axis because it's shorter in this case, and it gives us a co-vertex at 0b and another co-vertex at 0, negative b. So our major axis is our longer axis, our minor axis is our shorter axis. When we look at this, we are assuming that A is greater than B. That's why your book gives two different forms. I don't really like switching the A's and B's, but I'll do it just to stay consistent with your book. So if A is bigger than B, we know the major axis is going to be horizontal because it's going to be stretched out horizontally more. Okay? Whereas if the A is bigger and it's under the Y instead, now the major axis is vertical because that's being stretched out more than the horizontal axis. So here, this is the vertex, this is a vertex, and our co-vertices are still on the minor axis, but now it's horizontal. Okay. So we have vertices, we have co-vertices. Vertices are on the major axis, the longer one. Co-vertices are on the minor axis. No matter which way it's being stretched. We also have to talk about the fact that there are two foci. Okay, so here's a focus, there's a focus. They're at negative C0 and C0 if the major axis is horizontal. They're at 0, C and 0, negative C if the major axis is vertical. Now, where does this C come from? It's not in the equation up here. It comes from something that looks awfully like the Pythagorean theorem. We say C squared equals A squared minus B squared. And I'm not going to get into the entire proof of that right now. I'm not interested in that video. I just want to get you familiar with the ellipse, and we can look at that in the future. So that's how we're going to set it up. Okay, remember, we're calling the A squared the bigger one, so we have to notice where the bigger one is. It determines which axis is major, and then we can find all of these points and put together the picture of our ellipse. So on this one, let's find our vertices, co-vertices, foci, and then we'll graph it. So when we take a look at this, 36 is bigger than 12. So my A squared is 36, so my A is 6. My B squared is 12, so my B is the square root of 12, which is 2 root 3. All right? So if I were to be sketching this out, and I'm just going to do a rough sketch here. Again, the larger value is under the x squared. That's the A squared. So it's our major axis is horizontal. So I'm going to put a point here at negative 6, 0 as one vertex. I'm going to put a point here at negative, sorry, that was positive 6, 0. And I'm going to put a point there at negative 6, 0. Those are our two vertices on our major axis. Our minor axis is going to have co-vertices at 0, 2 root 3 and 0, negative 2 root 3. And our ellipse is going to look something like that. Okay? Now let's find the foci. And the equation that we use for that is c squared equals a squared minus b squared. So we have c squared, well, a squared is 36, b squared is 12, c squared equals 24. Take the square root, we get c equals, let's see here, what would that be? 4 times 6, so 2 root 6 is what we get for c. Of course, that's a plus or minus. There are two foci, one of them, and remember they're on the major axis, one of them is going to be at 2 root 6 comma 0. The other one is going to be at negative 2 root 6 comma 0. We found all of our information. We sketched a rough sketch of the graph. It doesn't look beautiful, but that's okay. Let's take this into using some of our technology to look a little bit more at the ellipse. So I'm going to go into GeoGebra actually. Okay, I'm not going to use Desmos for this one because there's some other things I want to do. And let's type in the equation of that ellipse. We had 36 there, right? And then we had, oops, what was our denominator there? I think it was 12. Let me just double check. Yep. Equals 1. So there it is. That's our ellipse. Let's zoom out just a little bit. Now notice, do we have vertices at 6, 0? There's that one. And at negative 6, 0. We saw those pop up there, blue points on our graph. Maybe I should zoom out just a tad bit more. We said our covertices were at 0. Let's see, come on. There we go, 2 root 3. And 2 root 3. Oops, let's see here, 0, comma, negative 2 square root 3. There we go. So now we have our vertices, we have our covertices. Now let's plot our foci. Those were happening at 2 root 6, comma 0. Okay, there's one right there. And our other one is at negative 2 root 6, comma 0. There we go. All right. So everything matched up exactly like what we said. It looks really nice. It's a really pretty graph. But let's explore a little bit more about one of the key features of the ellipse. Okay? Now, going back to a circle, we know every point is equidistant from the center on the circle, right? I could take a piece of string, pin it down, spin that string, and that's going to trace out a circle. And if you recall from what we learned earlier in our first introduction to conic sections, there's another thing going on here. So I'm going to put a point anywhere on my ellipse. So I'm going to put it right there, and I can put that wherever I want on the ellipse. But we'll just keep it right about there for now. What I can do is I can connect a segment from here to there. Okay, notice it has a length of 8.21. And then from here to there, that's G, it has a length of 3.79. So if I take F plus G, that gives us this number perfectly of 12. Now, what happens as I move this point around on my ellipse? Notice down here in the screen, you're looking at F and G. F and G are changing, but F plus G is still always 12. That the sum of those two distances are always the same no matter where we are on the ellipse. Okay, that's pretty cool. And the way we would draw this by hand is we'd take one piece of string, take the two ends, don't have them tight because then you can't do anything, slide them in so that string is kind of hanging down, okay, hold them together, and then put your pen inside that string and trace around like that, and you could create an ellipse all on your own. So I think time's up to wrap up this video. We looked at how we derived the equation of our ellipse from a circle. Okay, we understand what the two equations could look like. Remember then that A is always bigger than B, so we have to think about, are we stretching more horizontally or more vertically? We have these new terminologies. We know the relationship between C squared, A squared, and B squared, and we did one problem. So in our next video, we're going to look at a couple more.